And there were some questions that I got through emails actually quite frequently. And I was like, I don't understand why you guys don't see what I'm talking about. And it's because there's a difference between SPSS versions. So I've mentioned previously that I use version 25, but that's not the most recent version. That's just the one that I have in my videos um, from when I made them. So there is a discrepancy that might answer some questions. Some of you have emailed me and I've like gotten back to you, but the question is 2D for the bivariate regression between vertical jump and 100-meter time. So the question that a lot of you were asking is like, what do I report for this? And it's saying, what is the probability that there is no relationship between vertical jump height and 100-meter sprint time? So probability is indicating that we're looking at a p-value. So we need to find a p-value. That's like a good place to start. And then following that probability, we have a null hypothesis, right? So there is no relationship between vertical jump height and 100-meter sprint time. This is the null hypothesis for a bivariate correlation because we're only listing two variables and we're only interested in the relationship. We're not actually looking at the predictive factor, okay? So oftentimes on exams, like I could ask you or phrase a question in this way where I say, what's the probability? And then I list the null hypothesis. So that's like why you really want to make sure that you take note of your null hypotheses, right? But this would be the null hypothesis for a bivariate correlation. So that tells us we need to find the p-value for the correlation coefficient between these two variables. So in my output, you can see like vertical jump and 100-meter, that's the regression that I ran. And I have a correlation section. And in version 25, correlation matrices are always a part of regression analyses. So that's why for some of you, I was like, no, you just look for the p-value in the correlation. And then some people are like, I don't see it. And I didn't understand why until I met with a student earlier today. So really the answer to that question would be this p-value here, because it's looking at what is p, what is the sig value, right, or significance of this correlation coefficient, right? So the strength is a strong negative relationship, meaning that as vertical jump increases, 100-meter time would decrease, right? So it's inverse. And then the p-value for that relationship would be 0.000. You guys will remember earlier in the semester, I think I stated that whenever you see 0.000, usually that just means that SPSS has run out of numbers. So always report 0.000 as less than 0.001. Okay, so less than 0.001. And the reason is because p-values can represent the chance that we've made an error, and there's always going to be some small chance that we've made an error. So reporting it as 0.000 is just saying like, we are perfect, there is no error, which we know is not true. So I'm giving you guys that answer, and then I'm going to show you what actually pops up in the version 27, which I don't have installed on my computer, and I just saw that there was a chat pop bubble thingy, so I will come back to that. Anyways, when I plugged in all of this in the virtual lab, which has version 27, this is what shows up in the regression, and you'll see that the correlation matrix does not exist. And so that's why I think some of you, if you are using version 27, I don't know if it's the same for version 26, but that's probably why you had no idea what I was talking about when I was emailing you, because it just does not show up in version 27. And I think it's just for the bivariate regressions. If you ran a multiple regression that had multiple independent variables, you should have gotten a correlation matrix. But I think in this version 27, they cut out the correlation matrix for the bivariate regression because you get an R. So if you looked at this R value compared to mine in my output, they're the exact same number, but the only difference is that we actually get a p-value for this correlation coefficient in version 25. So I know this discrepancy now, which is why I'm giving you guys that answer for free, because I don't know what version everybody's using. But does that make sense, or does anyone have any questions on that? I need to get back to my chat bubble. That was question 2D.
How do we write that out? I texted in the chat thing.
So I can,
value?
yeah, it would be p is less than 0.001.
Oh, okay.
When p is reported as being equal to 0.000. Yeah.
Okay, thank you.
You're welcome. So I'm going to stop sharing and switch gears. But hopefully that helps some of you out. I felt like I maybe frustrated people. So I'm really sorry. I didn't know that was a thing. Okay. Let's do our memes because we need happiness. These are some funny ones that I found this week. I laughed at this as a child, but this is literally how I deal with life now. Relatable. Poor Lilo. I hope I'm not that old. Everyone's seen Lilo and Stitch, right?
Such a good movie.
It is great. But I mean, yeah, you just lock yourself in a room and just listen to music. It makes sense. Oh, chat, this is popular. Yes. I had a Stitch backpack for the longest time. I don't know what happened to it. Anyways, Stuart Little, hopefully everyone's seen Stuart Little before. Oh, honey, look at these poor orphans. We'll take the rat. And then Snowbell was probably like, oh yeah. Which is actually, this is actually just a zoomed in picture of my mom's cat. His name is Oliver. But I was like, oh. Response to this meme is just oof. Just one word. And then my last one, when I type I'm ducking mad, this is what I mean. It's a ferocious little beastie there. Okay. Anyways, hopefully you smiled. That's the goal. This week we are talking about t-tests. So if you loved correlations last week, you're just gonna love me more this week. I'm sorry. But t-tests, now we're kind of getting into, we're gonna have some repeated concepts from last week in terms of we're still gonna be looking at t-statistics. But now the t-statistics mean something different than they did last week. So when we talked about correlations, t was measuring the difference between the slope of a regression line for a sample, and we were comparing that slope to a population slope, which is why we use the standard error for B, or SEB, as we noted it in the lecture notes. So that was telling us how different is this regression slope, or how well does our sample predict this given dependent variable compared to what we would estimate a perfect model to predict in a population. Okay, So T this week is going to mean something a little bit different. And let's look at our decision tree to figure out what we're actually looking at. So we've kind of crossed correlations and regressions off our list. That's when we had both parametric dependent and independent variables. This week, we are switching gears. Our dependent variable is still going to be parametric data, so ratio or interval. For our cases, it's mostly going to be ratio. And then when we look at our independent variable, we have a non-parametric independent variable. So this would classify as nominal or ordinal. And for our purposes, our independent variables will always be nominal. So yay, nominal and ratio data. Those are basically the only two that you really need to know, okay? But once we've decided that our independent variable is nominal or non-parametric, we then have to look at how many independent variables we have. In a t-test case, as well as ANOVAs, we're only going to have one independent variable. However, that independent variable can have multiple levels or subcategories, which is why it's a nominal type of data. So if we were looking at different types of diets, diet would be the independent variable, and then we could have like different levels of that. So keto or paleo or whatever, like high carb all day, right? I don't know. So those would be different levels or different categories at which we are kind of separating our samples. Okay, so that's what levels means. So if there's two levels and only two levels, that's when we have our t-tests. If we have three or more levels, that's when we have ANOVAs, and that's what we're going to work on next week, which is a really nice expansion of conceptually, it's a nice expansion of t-tests, because generally the null hypotheses are very similar. We're just adding in more factors, okay? So parametric dependent variable, non-parametric independent variable, there's only one of those, and we have two or more levels of that independent variable, we get a t-test. And then, depending on the type of sample we've collected, we can have an independent t-test or a paired t-test. Paired t-tests are also called paired samples t-tests or dependent t-tests. And then another one that's not listed on here is a single sample or one sample t-test. And the reason we don't usually put it on here is because it's not super common, and we'll talk about why. But if you guys remember, between subjects means that we have different people in each sample that we've collected. Within subjects means that we are using the same people, or we're repeating measures on them, okay? Paired t-tests can also be used if, I don't know if you guys have ever read any articles that use a paired t-test, but you could have age-matched individuals or people who are matched by BMI, or people who are matched by a list of factors. So BMI, height, like you're basically trying to make an identical person. If you collect the exact same person, it's pretty much the same thing. So those are two different ways we can do it within subjects design.
Hey, Natalie.
Yeah.
At the beginning, you said independent variables will always be nominal and dependent will always be ratio, right?
For our class, yes.
Okay, thank you.
The only exception might be if we have interval type dependent variables, if we're looking at joint angles, because that's, we know angles can range from negative values through 0 to positive, depending on like what joint we're looking at. So like the hip, for example, could be 0 in a neutral anatomical position, but has a positive angle in flexion, but a negative angle in extension. So
and that would be interval?
That would be interval. But that's
Gotcha.
the only example I can think of that we're going to run into later in this semester. That would be interval. So if you can always like just be on the safe side, and if I ask you what type of variable is this, you can just put parametric or non-parametric, because those just kind of encompass everything. And those are also acceptable answers. So it's kind of up to you, but yeah. So this is our decision tree. And now we just need to know why we actually run the t-test. So we do this when we want to know the effect of some manipulation, intervention, or exposure on two levels of an independent variable, right, on a given dependent variable. So remember, the dependent variable is what we measure. The independent variable is going to contain some type of manipulation that the researcher wants to know, right? So really what we're doing is we're just determining the odds that two group means are equal to each other, or we're finding the probability or the p-value for a comparison of two means. So we know two levels of an independent variable mean that we have two samples, right? If it's a between sample group that's two different sets of people, if it's within sample, it's the same people, but they're just measured under two different conditions, right? And we just want to know, are each of those conditions the same, or does the intervention do something to significantly change the dependent variable such that those conditions are different? So we can do this, like I said, with two samples, which is more common in kinesiology. Or you can also do this by looking at, a single sample compared to a population. So we've noted previously that it's very rare to actually get an entire population. But if you have like a test, I think I gave you guys an example of this actually a little while ago. It might have been a couple weeks ago. We were like, oh, the Thomas test is a very well-known and widely studied mobility or flexibility test for the hip flexors. So it's kind of been established that this is the mean, or this would be the norm for a given population or given athletic population, right? So things like that, where something has been studied so extensively that you could probably estimate a norm value, which could be like an estimated population value, could work for a one sample t-test. Also, if you have like a disease that's really, really rare, and the likelihood of you gathering everyone who has this disease is probable, then you could also run a one sample t-test and say that you have an estimate of the population. But again, one sample t-tests aren't going to be as popular just because it's harder to estimate the population without an extensive amount of data. So we're comparing means. That's kind of the overlying reason for why we run the t-tests. We want to know, are two groups similar or are they different? And in order to do this, we have to calculate a t-statistic. But like I said, it means something different than it did last week because stats isn't confusing already. So when we're looking at a t-statistic for a t-test, we're wanting to know what is the mean difference between our two samples. So that would be this example over here. Or if we're looking at the difference between our sample and an estimated population mean. Okay. So what is the difference in the sample that we've collected, and how would that mean difference be projected onto a population, which is what standard error does, right? Because standard error is just the standard deviation of a population, pretty much. So we're still doing our statistical inference, where we have sample characteristics divided by some population characteristic that we think we might get. And that's how we are able to infer sample information onto a population, is because we build in both of those things into our actual equation. Okay, so like I said, t-statistic for a single sample would be the sample mean minus the population or estimated population mean. If you're looking at the mean difference between two samples, right, it's just sample 1 and sample 2, or the means of sample 1 and sample 2. And this can be used for both between or within subjects. You just have to know what the means are. Okay. And then just one more time, because it's important, T is something different than what it represented for B. Okay. So T for a B coefficient is for regressions. T for a t-test, right, or T statistic for a mean difference is for our t-tests. So now we can talk about different types of t-tests. But before I do that, does anyone have any questions before we move on? Okay, let's talk about these. Basically, I'm gonna just keep saying the same thing over and over again today, but we'll just have different examples and different small differences in characteristics of our samples. But the concept of t-test is all the same. You're comparing two means. It just depends on where the means are coming from. So we have single sample t-tests, independent t-tests, and dependent or paired sample t-tests, which we already mentioned. Okay, the assumptions for our t-tests, we have our golden two that always have to exist for any statistical test, and that's that you have a normally distributed population, right, in terms of the dependent variable. So when we take the measurements for each of our groups and plot them in a distribution, we need that to be normal. We also need to make sure that our sample is randomly selected. That will help give us better chances of our sample being normally distributed. And then third assumption is the characteristics that we need to run a t-test, which were in the decision tree, right? So we need a parametric dependent variable and a non-parametric independent variable that has only two levels. I emphasize only two levels, okay? And then usually we have a fourth assumption that has to be met based on the type of sample. So if there are two samples and you're not looking at a single sample t-test, if you have between subjects or between subject design, we add on the assumption of homogeneity of variance. And we'll explain what this is when we get to the independent t-test discussion. And then if you have within subjects, usually you have to have a certain correlation coefficient between both of your groups to make sure that you can assume that each group has been collected on the same person, if that makes sense. Or like control versus intervention. So we'll get there. But these are two additional assumptions that you would add on based on the type of sample that you have. We also, if we're looking at sample kind of projected onto a population, we have to talk about degrees of freedom. So last week, degrees of freedom for regressions were n minus the number of variables that you had. This week for t-tests, it's n minus the number of samples. Like I said, we love statistics. It's not complicated. It really isn't. Okay. So degrees of freedom for t-tests is n minus the number of samples. So if you've got a single sample t-test, your degrees of freedom are n minus 1. That should make sense because you only have one sample, right? If you have an independent samples t-test, you have two independent samples. That means two samples total. So you would take the total sample size, meaning you sum the two samples together. So if I had 10 people and 10 people, my total sample or total n would be 20 because I add those two together. And then I subtract the number of samples that I've collected from, which would be 2. So if I'm using a total n of 20 minus 2 samples would give me a degrees of freedom of 18. Okay. For a paired samples t-test or dependent t-test, it's the same thing. Degrees of freedom is n minus the number of samples. Okay, so in a paired t-test, we use one repeated sample. So if I had a total of 30 people that I've measured twice, still only one sample, right? 30 would be my total, n minus 1 would give me degrees of freedom of 29. So we'll bring these back when we've got some like sample outputs to look at so you can see how they're calculated. But those are kind of like assumptions, and degrees of freedom are kind of two things that are overlaying every single type of t-test. So that's why we're talking about them first. Okay, so let's talk about our single sample t-test. Just a reiteration, we're going to use this when we're comparing a single sample to an estimated population parameter. So we have an estimated population mean. We've got enough data collected that we can confidently say this is probably what the norm value would be for a given population of interest. Okay. So our goal with the single sample t-test is to say, is a sample that we've pulled from this population significantly different, or is it equal to the population we pulled it from? And we mainly are doing this to see if the sample was actually drawn from the population. So if I have, let's use Thomas test for our example, measures hip flexor flexibility. And I think the norm for that test is like 20 degrees below horizontal. So let's say that that was my my estimated population mean is 20 degrees, right? And I take a sample that, let's say that 20 degrees is from an athletic population. So I'm like, ooh, I need a sample of athletes then. And I take a convenient sample of like volleyball players and then compare their Thomas test mean to the estimated population mean. Okay, to see, are these people actually representative of the population that we drew them from? So that's where that last point comes from. But all of the, I know it's a lot, I'm so sorry. So the t statistic or the t ratio, those are interchangeable terms, right? We already presented this on the previous slide where we're looking at what is the difference between our sample and our estimated population means. And then we have to divide that by some standard error in order to relate that sample characteristic to an expected population characteristic. So that's how we get an actual mean difference divided by the expected mean difference. Okay. SE sub m is our standard error of the mean. We've seen this before. And that's just the standard deviation divided by the square root of the sample size. Okay, so we could calculate this if we know these two values. And we can calculate the numerator, obviously, because we have those bits of information. That gives us a t statistic, which we can then compare to our t table. Okay, now some of you had some good questions via email on like, what is the t, like when do we use the t table versus when do we just use the SPSS output? The t table will give you an estimated p-value. So if I explicitly ask you like, use this t table, or if I ask you like, find the confidence interval, like you would have to use the t table in order to get a critical value. So usually if I say, what's the estimated p-value or find a confidence interval or something related to one of those two things, you're going to need to use the t-table. So if we were estimating a p-value for a single sample t-test, and we had these bits of information to calculate a t-statistic, we could say, how does that t statistic compare to a critical value? Remember, we figure out what the critical value is based on our degrees of freedom and our level of confidence that we've chosen. So if I chose a 95% level of confidence, I'd find that column in the t-table, and then I would use my degrees of freedom, which in this case would be n minus 1, and I would find like the intersection point of those two values to get the critical value, which is just representing how large of a difference do I need in order for significance to be met at that given level of confidence with this given sample size. Okay, so similar to last week, if t is greater than the critical value, t, remember, is looking at what is the mean difference, what is how big is the difference, right? So if t is greater than the critical value, that means that the difference between our means is large enough that we can consider these means to be significantly different from each other. So if t is greater than the critical value, we usually reject the null and we say that p is less than alpha, whatever alpha is. Okay, so if we have a 95% level of confidence, we would say that the estimated p-value is p is less than 0.05. If we had a 99% level of confidence and we found that t was greater than the critical value, we would say that p is less than 0.01. I can do math. Okay. So that's how we estimate significance or estimate p-values. If we're using SPSS, they just give us one and we say thank you and we're done for the day. Okay, so that would, SPSS gives us exact p-values. Using the t-table will give us estimated p-values. And then we can do a confidence interval. So this should look very similar to a lot of the other confidence interval equations that we've looked at so far. And this would be the confidence interval for what we are estimating the true mean to be based on this comparison up here. Okay, so we can take our sample mean and we say, what is the difference, or what is this critical value that exists in the table at a certain level of confidence for given degrees of freedom, times the standard error of the mean, and then we can figure out what's the interval for a true population mean given some sample mean, or where would we expect the true mean difference to exist, is another way of saying that. So this is different from the z-score confidence interval that we gave before. That one we had a mean plus or minus the z instead of t, right, times the standard error of the mean. So this one, because we're looking at a t statistic, is saying where would the mean difference lie, basically. The other one is looking at where the true mean of the population would exist given certain sample characteristics. So I write this out a lot better in the key concepts and terms thing in the supplemental section of this week. So if my words just went bleh, I don't know, you can look at that and it's like written out so you can distinguish the differences. But this is kind of like the nitty-gritty of a single sample t-test. So does anyone have any questions on that? Sounds good? Okay. So what are the null hypotheses? Because that's really what we're answering when we find a p-value, right? So we refer to, at least, I think this is this is the week where things start to get confusing. Actually, last week is when things start to get confusing. This week is when they start to get really confusing. And then usually by next week, you guys are like, oh, this is butter. Anyways, so this is the main effect. Okay, this is the t-test, the null hypothesis for a single sample t-test. Okay, and what we're interested in is, does the independent variable treatment have an effect on the dependent variable, right? So when we're looking at a single sample, we can say we drew them from the population. We know what the population mean would be, but let's like expose them to something and then see if that exposure is different. So if we're using the Thomas test example, we could say this is the norm for an athletic population, and then take our sample of volleyball players arbitrarily, right? Take our sample of volleyball players and then say, let's do a stretching program with these people to see if we can change their hip flexor flexibility. And then compare them to the population norm and say, do we actually think that this hip flexor or this stretching program actually had a significant effect on their hip flexor flexibility outcomes? Okay, so does a treatment have a significant effect on a dependent variable when you're comparing a sample to an estimated population mean? We can also word this another way. So all of these mean the same thing. They're just different wordings, okay? So we could say the difference between the means of the treatment group and the population, which is kind of like our control, is not significant, right? Or the means are equal, okay? The treatment group, which is our sample, is not significant from the population control, right, in terms of the dependent variable measurement, and thus can be considered to be representative of the sample, or be a representative sample of the population. So all kind of drawing back to the points that I had on this slide. Okay, so wording is up to you. This first one is my favorite one because it's very formulated. Is there a significant effect of the independent variable on the dependent variable? Yes or no? Okay, so I feel like you can use this one very easily, but if you like saying the difference between the means, whoa, like that's totally fine as well. Okay, so these are different null hypotheses. Again, they all mean the same thing, referring to the fact that our means are equal to each other, because we can't prove that two means are different unless we actually prove it with a p-value, okay? So all of these are saying that our sample is no different than our population, or estimated population. So let's look at an example because that helps. If we wanted to look at the effect of that was actually very unintentional that I just chose volleyball players and stretching, because I forgot that this was the example I gave. So if we look at a 12-week training program on ankle sprain injury rate in volleyball players, we would identify the independent variable as the training program. Okay, so our experimental sample, we say, let's take a bunch of volleyball players. We know the national ankle sprain injury rate for some reason. We know that information, right? And so that would be like our control group, is what is the national average? And then we take a sample of volleyball players, give them this 12-week training program, measure their ankle sprain injury rate at the end of the program, and then compare the mean of the sample to what the known control is, or what the known injury rate is. So that would be our dependent variable, which is what we're actually measuring. Okay, so if we were using a two-tailed test, right, meaning that we could have significant differences above or below the mean, right, then we would have these examples of null and research hypotheses. So the null hypothesis, again, would say that our sample mean is equal to our population mean, right? Or the difference between the two of these would be 0. They're not significantly different from each other. Training program has no effect on ankle sprain injury rate, right? Versus the research hypothesis, which argues the exact opposite of the null, saying that there is a difference. Doesn't matter if ankle sprain injury rate increases or decreases. We just know that there is a significant difference between the means. Okay. So, anyone have any questions on this example? Cool. I feel like this part is more or less pretty straightforward. It's when we start throwing in other assumptions that all hell breaks loose. But I've given you guys some practice problems. There is an Excel spreadsheet listed in the lecture section of this week that has all of the practice problems included in it. They're already formatted for you, and I have a video that goes through or like walks you through how to do the practice problems if you want to follow it and check your answers. But these will be on that, so I'll skip over those for now. But these will just give you practice finding estimated p-values with your t-table, and then using that t-table also to find confidence intervals, which all of those equations are on this slide. So you have been given everything. So what do one sample t-tests look like in SPSS? Honestly, this is like one of the simplest outputs you will get, other than like the mean and the frequencies analyses that we did at the beginning of the semester. So we'll get descriptive statistics, which is just telling us how many people we had, what's our mean, what's our standard deviation, standard error of the mean. Sometimes they might throw in other things, but these are like the core bits, especially sample mean standard deviation. We have some variable that or characteristic of our sample that we've identified in SPSS. This is an example I took off the internet, so I don't even know what this is referring to. I don't know what DEP stands for. But then we have the main effect output, which will show up as a one sample test. The test value on the top is going to be what we've identified as our estimated population mean. And then within our table, we have our t-statistic, which is calculated by looking at the differences between the means divided by the standard error. So if I took 4, or the difference between 3.7225 minus 4 and divided it by this standard error, I should get something close to this t-value. Okay. Degrees of freedom is 39, which should make sense because we only have one sample, right? So 40 minus 1 gives us 39. And then SPSS gloriously gives us our p-value, which tells us if we have a significant difference or not. I think I have to sneeze, but I might have just jinxed myself. Okay. So in this case, if we were using a 95% level of confidence, which from this point on, that's usually what we're working with. So just always think, is p less than or greater than 0.05, pretty much. We can see here the exact p-value is 0.022, which is less than 0.05. So we would say in this case that whatever this sample is, right, they are significantly different from the estimated population mean that we think we had. They indicate what the mean difference is. So if you took 4 minus 3.7225, you should get this value here. And then they tell you what the confidence interval is for that mean difference. So again, that's where your confidence interval using a t-statistic versus a confidence interval using a z-score is different. This tells you what the confidence interval is for the mean difference between a given sample mean and what the known population mean would be. Okay, so you can see this mean difference does in fact lie between these two values. Okie dokie. Are we okay on one sample t-tests? Can use your participant reactions, yay, nay, just to check in. Thumbs up, that's cool. Oh no. Okay, well, I would love to say it gets better. We can talk about independent t-tests now. So instead of working with a single sample in a population, we're going to look at two samples with a between subjects design. So that means we've collected, let's say I wanted to compare our stats class to Dr. Wu's stats class, because both of us teach different sections, right? We could say, what is the average GPA of people who take stats? And I can take the sample of our class compared to the sample of Dr. Wu's class. And I know our class would have like way better scores, but that's biased. Anyways, that would be an example of between subject comparison, right? Two separate samples, two different sets of people. Okay, we want to know, are they actually drawn from the same population? So in our case, is the mean GPA of our class equal to the mean GPA of Dr. Wu's class? It's basically what we would be doing for that example. Null hypothesis obviously would say that there is no difference between the classes. Okay. So we can still apply this whole t ratio, t statistic. We just change the variables that are in the equation. So the concept behind the t statistic is still the same. We want to know what's the actual mean difference within our samples. So let's use our stats class, right? So let's say mean of sample 1 is our class, and we want to know what that difference is from the mean of sample 2, which would be Dr. Wu's class. And then we divide that difference of our samples, and we're inferring it on what we would expect the actual mean difference to be in a given population. And we call this the standard error of the difference. Okay. So this can be calculated by looking at the square root of the sum of squared standard error of the means for each sample. It's very difficult, but you can see standard deviation divided by, usually we see the square root of n, right? That is our standard error of the mean. So basically, right, this is squared. So if we pulled this little chunk out, it would be standard deviation divided by square root of n. Okay. So we're basically looking at what is the sum of the standard error of the means for each sample. We just write it differently. For you guys, I think in the examples I give you, I give you the standard error of the mean values, so you don't have to calculate them. But you have these two options. That way, if you did have to calculate standard error of the mean in this square root, you could. Okay. But once we figure out what our t-statistic is, right, using the standard error of difference and the two sample means that we've collected, we then can compare that t-statistic to a critical value on our t-table. If t is greater than the critical value at a given level of confidence at a given degrees of freedom, which in this case is total n minus 2, right, then we can say we reject the null and our p is less than the alpha that we set when we started writing our stats. Okay. So again, I think if you want to think about it as total n, or the total sample size of everyone who's been included, then you can think of it as total n, but it's really the sum of both samples minus 2. We derive that from basically taking 1 degree of freedom for each sample. So that's where the minus 2 comes from. We can also calculate a confidence interval for this, which is basically the exact same thing as the single sample t-test confidence interval. So we just want to know what is the true mean difference between these two samples inferred onto a population, right? So if both of these samples were from the same population, we would expect this mean or the true mean difference to be very, 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 very small. Okay. If these two samples are significantly different from each other, the true mean difference of our confidence interval, or that we display in our confidence interval, is going to probably be a little bit larger in value. Okay. The actual size of the interval is just going to be dependent on certain characteristics that we've talked about before, right? So sample size can affect confidence interval size. The level of confidence could affect interval size, et cetera, et cetera. But we're really just trying to find out what is the true mean difference within a population setting. So we look at the difference between the samples. We use the critical value from our t-table at a given degrees of freedom, given level of confidence, and then we multiply that by our standard error of our difference. Okay. Questions on the math in this one? Okay, so let's talk about our null hypotheses. For an independent t-test, there are 2 nulls that you have to know. One of them is for the assumption. One of them is for the main effect. We're going to do the assumption one first. Okay, so you remember in the assumptions list that I gave you, we have normal distribution, random sampling, our variable characteristics, so parametric dependent variable, 1 independent non-parametric independent variable with 2 levels, and then there were the extra little tidbits at the bottom based on the type of sample we've collected. Okay, so when we have between subject design, we have to look at an assumption called homogeneity of variance. Okay, if we break this wording down, homo means same. Variance is just referring to how spread out the data is. Okay, so it's more or less a comparison of our standard deviations. I've never really looked at the formulas that go into how this set of statistics are calculated. But if you think about it, it's just how different are your samples, and are they too different to compare to each other, or are they similar enough that they can be compared to each other? So homogeneity of variance has its own null hypothesis. We test it using Levine's test in SPSS, and I think that will show up in one of the output examples that I have today. But we use Levine's test to look at homogeneity of variance. And basically what it's arguing is very similar formula to the other null hypotheses we've seen before. Homogeneity of homo, same, variance. That's the null hypothesis. The variance in group 1 is relatively equal to the variance in group 2. Same variance, equal variance. Okay. For assumptions, we always want the null to be true. Okay, so that means a p-value greater than 0.05 is what we're looking for when we have a null hypothesis for an assumption test. The reason this is we cannot accept the results of our main effect unless we have met all of our assumptions. Okay. So if our variances between our groups are not equal, usually there is a correction factor that is applied by SPSS. And typically what happens is it will change the degrees of freedom. And then that will kind of correct for the fact that our variances between our samples are too different from each other. It will make them more similar so that we can accept the comparisons between the groups. Okay, so homogeneity of variance, equal variances between groups. That's at least what the null would say. We want a p-value greater than 0.05 to let us know that the variances are not significantly different from each other. Okay. The null hypothesis for the actual t-test or the actual main effect is similar to the single or one sample t-test we looked at before, where the independent variable or the treatment or exposure, intervention, whatever, right? Whatever our manipulated variable is, it has no effect on the dependent variable outcome. We could reword this to say that the difference between the means of group 1 and group 2 are not significant. We could also say that the mean of group 1 is not significantly different from group 2. Thus, both samples belong to the same population. The means are equal. There is no significant difference. Okay. So let's look at our same 12-week training program ankle sprain injury rate example. Let's say for this one that we don't know what the national average is for volleyball players in terms of ankle sprain injury rate. So we're going to collect 2 samples instead. We'll have one sample be our control sample. So let's say we randomly select 20 players and they just go on as normal. They don't receive the training program. And then we're going to have an experimental sample, which we're calling sample 2. And we take another 20 players who do receive the 12-week training program. So going into this test, we're basically assuming that each of these samples is representative of the population, or we're assuming that they're equal, right, to each other. And then we're going to see, does this training program have an effect on our experimental group such that they have a higher ankle sprain injury rate, or such that they have a lower ankle sprain injury rate, right? And again, ankle sprain injury rate is our dependent variable. So
This type of data
sorry, what?
between this type of data selection would be like between sample groups.
Yeah, because we have 2 different sets of people. They're independent samples. Yeah. So our hypotheses would be very similar to what we saw for the one sample t-test, right? Where null hypothesis says that the mean ankle sprain injury rate is the same for both groups, regardless of the training program. Research hypothesis would argue the exact opposite, saying that the training program is going to have some effect on ankle sprain injury rate, right? Or there's going to be some difference in terms of the injury rate. We're not specifying above, or like if we're having an increase rate or a decrease rate, we're just saying there is a difference because it's a 2-tailed test. Okay, so that just puts some variables and sample examples together for an independent t-test. And then similar to one sample t-test, I gave you guys some examples to work with. Let's see. Yeah.
Can you explain the difference between the homogeneity of variance assumption between the main effect?
Yes. So the main effect is looking at if the sample means are equal or not. The homogeneity of variance is looking at if the variability in the samples is equal or not.
Can you say it one more time? Sorry, I'm writing it down.
So null hypothesis for the main effect is is looking at if the sample means are equal.
Gotcha.
And the null hypothesis for homogeneity of variance is looking at if the variability between the samples is equal.
Thank you.
Really, if you think about it, we want the standard deviation or the variability within each sample to be fairly similar. So we have some sample mean plus or minus, let's say, I'm going to pick a number. Let's say our standard deviation is 3.4 for sample 1, and it's 5.7 for sample 2, right? SPSS is going to tell us if that variability is going to make a difference on our results or not. Which is why we usually implement corrections to the degrees of freedom, because that's kind of a direct manipulation of the sample. So, yay. What does this look like in SPSS? I know these values are super, super small, but it's the spatial location that you're kind of paying attention to. But this was the best figure I could find on the internet. So in the output, we still get our descriptive statistics, but instead of getting descriptive statistics for one sample, we get it for 2. So this particular what do I want to say? This test, I guess. We're looking at comparisons of height between 2 different types of people, I'm assuming. Okay. For our first group, we have 7 people. Second group, we collected 6 people. We have the means of each of those groups, the standard deviations, and the standard error of the mean. Okay. Before we can even look at if the means are equal or not, right, which would be the main effect of the t-test, before we even look at that, we have to see, did we meet our assumption? So homogeneity of variance, remember I said, is tested using Levene's test. That's what this is right here in this red box. So you start here, okay? Because again, we can't accept the results of our t-test unless we've met all of our assumptions. But we can't meet this assumption until we actually run the statistics. So you'll see that there are 2 rows in this table. There's equal variances assumed, and there's equal variances not assumed. Okay, so I know this is still fresh for you guys, right? But this is going to be our homogeneity of variance assumption exact p-value, right? Sig, remember, always resembles a p-value. So p in this case is 0.790. Using your participant responses, do you guys, you put a yes or a thumbs up if you think we've met our assumption? Put a no if you think we have not met our assumption. I'll give you a second to think about it. Seeing yeses and thumbs up. That's good. Yeah, okay. So we have met our assumption because p is greater than 0.05. Remember, assumptions, we want p to be greater than 0.05. That means we have equal variances between our groups, which means that they're comparable enough. And you can see that in the standard deviation, right? 1.9 compared to 1.7. Those are fairly equal to each other. So this means that if we've met our assumption, we can move on to actually obtaining the p-value for our t-statistic, which is what we're really interested in. Okay, so we've decided that we've met the assumption, or we can assume equal variances. So that means we're going to read this top row where we can see our t-statistic, our degrees of freedom, and our p-values. Okay, equal variances assumed means we read the p-value for the top row. And do we have a significant difference between the means or no? So use your participant responses. Significant difference between the means or no? I've broken you. No one's responding. I see a yes. I'll give you a hint. Let's say we were using a p-value of, or an alpha, not a p. We're using an alpha level of 0.05. Do we have a significant difference between the means? Yes or no? It's okay if you take a second to look through your notes. Oh, and someone put something in the chat. We have a no, a couple no's. Does anyone who said no want to explain why? You're correct, so don't freak out. No one wants to explain why they were right. Okay, that's fine.
Yeah, because actually for the so the p-value is greater than 0.05, so it's 0.269 it looks like, so we wouldn't accept, or it wouldn't be a significant difference.
Right. Okay, because remember the null hypothesis says that the means are going to be equal to each other or relatively equal to each other. So if our p-value is greater than 0.05, that means we have a high probability that those means are actually equal. Right. Conversely, we can also say that there's a high probability we've made an error. Who just spoke up?
I just said, so you'd accept the null then right there?
Exactly. We would accept the null because p is greater than 0.05. Right? That relationship, if p is greater than 0.05, you always accept the null. If p is less than 0.05, you always reject the null. But you just have to know what is the null hypothesis that you're accepting or rejecting. Right? So in the homogeneity of variance case, p was greater than 0.05. So we would accept the null hypothesis for our homogeneity of variance, which says that there are equal variances between our groups. Right? For this one, p is greater than 0.05. We accept the null hypothesis, which says that the means between the groups are equal to each other. Okay.
But I thought for the homogeneity, you want the null to be true.
You do.
Oh, okay. I see what you're saying now. I see what you're saying.
Yeah.
So you want it to be greater than 0.05. All right.
Yeah. Usually when you apply some type of intervention, you want to see that the intervention had a significant effect. I did make a comment, though, a couple weeks ago that insignificance is not always insignificant. So having a p-value of your main effect be greater than 0.05 is not always a bad thing. You're just showing that there is no effect. Like you've proven something for other research to build on.
So then relating it back to our example about the 12-week training program for like the ankle sprain rate, you would say it would mean that the sample populations were equal, meaning that doing the protocol, the training program didn't affect their rate of sprained ankles.
Right.
Gotcha. Okay.
Yeah.
And then also another comment. So since the homogeneity of variance assumption p-value, since that was significant, we only look at the top one then, right? Saying they're equal. Like we'd only from there on out, we'd only look at the top row.
Right. But
like the T, degrees of freedom and stuff.
Mm-hmm. Yeah, but this one is not significant because it's greater than 0.05.
Oh yeah, but that's what we wanted. So
yeah, that's what we wanted, and then that will tell you which row to read. So if p was less than 0.05, then you would say equal variance is not assumed, and then that's when you would read this bottom row instead. Okay. So, yeah, and I go over this again in the activity for this week, and I also go over it in the flowchart videos for the t-tests, which I think might be a little bit helpful in sorting out what your null hypotheses are for this week, because there's a lot. But you can see like the degrees of freedom changed. And that's a result of whatever the correction factor that's done by this test when the assumption is violated. Okay. But we can see the mean difference is literally just the subtraction between the means. Oh, go ahead.
Would you accept or reject the whole, or like how would you relate this now to the exam? You muted yourself.
Okay, never mind. I got it now. It's fine. It's Monday. I got kicked out, so I didn't hear what you were asking, JT.
I was just saying, like, how would you ask us a question like this on the exam? Would it look like just like a table, an image of a table like this, and you'd say, would you accept or reject the null, or would we have to find the homogeneity and then go from there? Like, how would you ask us this on the exam?
Yeah, so the activity sets up a good format on how I would ask questions. So typically, something is related to identifying the independent and dependent variable characteristics. And then I'm still wrestling with how I want to do the exam, because the exams are basically like activities. At least they take about the same time that activities usually do. So when last spring, when we transitioned to being online in the middle of the semester, I gave students the outputs. Last semester, I did the exact opposite, and everyone ran their own tests in SPSS. So, and I've gotten good results both ways. So I might just do a mixture this semester where I give you some outputs and then other tests you actually have to run. So,
Okay.
yeah, if I don't, basically I would say like,
So no at all.
but pretty much, yeah.
All right.
I'm sorry. But like, regardless if I gave you an output versus if you had to solve it, you'd still need to know where to find the information and how to interpret it. So, usually for the assumption, I would ask you, like, what is the probability that we have equal variances between our samples? That's asking what's the p-value for homogeneity of variance. Or I would say, did we violate homogeneity of variance, or is it assumed? That's kind of like a yes or no. What's the p-value? And then you list the p-value. For the main effect, I would say like, I could say what's the probability that the means are equal, which is saying what's the p-value for the t-test null hypothesis. What did the intervention have a significant effect on the dependent variable? Yes or no, what's the p-value? That type of thing. Typically, it's all going to be focused on the p-values. I don't usually ask you too much about the t-statistics or the degrees of freedom in the outputs. The only time you would have to calculate a t-statistic is if you're if I explicitly ask you to calculate a confidence interval, or if I ask you to estimate a p-value using the t-table. But yeah, outputs.
Thank you.
Yeah, usually centered on p-values. That was probably a lot more information than you were looking for, but
No worries.
All right, so those are independent t-tests. Any other questions before we move on to our dependent paired sample t-tests? Okay. I think we're okay. All right. So dependent or paired samples t-test is exactly the same as an independent t-test. The only difference is that we use the same people to collect on. Okay. So we can have, like I said, paired samples can be a couple of different things. Usually in kinesiology, we will use the same person, which we call a repeated measures. But like I mentioned before, you can also match people based on a certain characteristic. So like if we were using twins, identical twins, they would be considered a paired sample because they're basically the same person. At least from a genetic standpoint, typically is why they're paired. But we could also, if we're looking at like Parkinson's disease and its effects on gait variability, we could take age matched controls that are healthy to see that, that way we kind of like cancel out the age factor. So paired samples can be repeated measures using the same people, and you're just measuring them more than once, or it can be people that you've assumed are the same based on a certain characteristic. But the whole thing again is we want to see, given some intervention or difference between the samples, are they from the same population, or are they significantly different from each other that they represent different populations? The math behind all of it is pretty much the same. So we're looking at the actual mean difference between our samples divided by the standard error of the difference. This equation gets a little bit more complicated. So you can see that this first part is pretty much the same as what I gave you for an independent t-test. We just factor in this little extra bit at the end, which is trying to kind of correct for the fact that we have paired samples. And you'll see that there's an R snuck in here. We'll talk about that on the next slide. But if you recall in the assumptions list that I gave you at the beginning of the lecture, I said that within subject designs needed a correlation, or needed to have a certain correlation factor. So the concept of how you get the t-statistic is still the same though. It's the actual mean difference of the sample divided by what you would expect the mean difference to be in a given population. Once we calculate that t-statistic or the t-ratio, right, we can compare it to the critical value on our t-table if we're estimating a p-value, right? If t is greater than the critical value, we reject the null and say that p is less than the alpha we've chosen. In the case of a paired samples t-tests, if we are using a single sample, we do degrees of freedom n-1. For all of the examples I give you guys in this class, the people that you're collecting are going to be a repeated measures design, so you're just measuring them twice instead of having like identical twin situations. But the confidence interval would tell us what is the true mean difference between these two samples that are projected onto a population. So same interpretation as an independent t-test, just slightly different ways to calculate things.
Hey, Natalie,
Yeah.
you said at the beginning repeated measures using the same people for paired samples.
Yeah.
Okay.
So let's talk about this R thing in here. Okay. So this is, again, this is the correction factor, kind of popping in a correlation between the two samples. So typically, I'm just gonna pop this forward. Typically, there will be some correlation coefficient reported in the output. I couldn't find an example of this on the internet when I was trying to like copy paste images. But I do show it in, I think I do show it in the flowchart video, and I think I also show it in the activity video. It's also something you can easily calculate in Excel, right? By taking like the CORL function and then taking the dependent variable measures for your two samples. But really what we want to see is that your samples are strongly correlated to each other, specifically with an R that's greater than a value of positive 0.8. No negative correlations. And the reason why we want a positive 0.8 is so that we can say that the pre and post measurements, right? Usually when we have repeated measures, our sample is both the control and the experimental group. So this just will tell us basically that we have homogeneity of variance or not without actually calculating the homogeneity of variance, because homogeneity of variance can only be calculated on independent samples. But basically this tells us that as we measure whatever our variables are, let's say our dependent variable for our control group and we have a dependent variable for our experimental group. Both of these are ratio data, which is why we can create a correlation, right? But we basically want to see that variation in our control group is similar to variation in our experimental group. So as, let's say if we were looking at flexibility, right? If I was the subject, my flexibility increases based on some training program are going to be based off of my start position or my baseline measurement, right? So if I start out super flexible and I have this training program and I increase flexibility, right? As my baseline flexibility increases, the training program effect should also increase. I shouldn't see a reverse effect where the training program would make me less flexible, if that makes sense. So this just ensures that the variation or the deviation that we see from a control measurement to the actual intervention measurement are, I don't want to say increasing, but they're deviating at the same amount, which means that the variability between each measurement is relatively the same. So R, in this case, for paired samples is very similar to the homogeneity of variance assumption. We just don't have the special test for it. We just say, is R greater than or equal to 0.8 or positive 0.8 specifically? And if yes, then we've met that assumption and we can move on. Okay. All right. So for our two-tailed null hypothesis, for our paired samples t-test, this is our main effect again. Main effect for any t-test is that the means are equal. Treatment had no effect. No significant difference between the means. The means or the samples come from the same population. I literally told you I would be saying the same thing over and over again. So hopefully this is starting to sound familiar. Okay. If we put this onto our 12-week training program and injury rate, right, for ankle sprains, if we were doing a dependent t-test, that means we'd have likely a pre and post measurement. So we would collect our 20 players and we would say, let's look at what your average ankle sprain injury rate is over the past X number of years. That would technically be our mean injury rate for that sample specifically. And then we would give them this training program for 12 weeks to see if that injury rate changes at all. Okay. So dependent variable is still the same. It's what we're actually measuring. The null hypotheses are still the same as previous examples, right? Means are equal. for the null, means are not equal for the research hypothesis. Meaning, training program has no effect for the null hypothesis. Training program has a significant effect for the research hypothesis. So I've included sample problems for these ones too. So you guys can practice those in the practice problem set if you wish. And then for this one, what I did is I have it so that you run the statistics as a paired t-test versus an independent t-test. So that means you're kind of fluctuating the samples a little bit differently. But I just wanted you to see what the difference is in the outcomes. Because paired t-tests are usually, I don't want to say they're always better, but usually you have better homogeneity of variance. So you can, in a between subject design, a lot of times you're just trying to see, or you're assuming like these samples have been drawn from the same population. If we plotted them on distributions, they'd both be normally distributed. They basically have everyone is matched in some way without actually matching people. So there's a little bit more error that can be made with a between subject design, which is why paired or repeated measures designs are often encouraged. But just because you have a repeated measures design doesn't always mean that you're going to end up with a significant difference. The same goes for between subject, but usually one is harder to prove significant than the other. So that's what I wanted you guys to look at by kind of doing this comparison in the practice problems. And then the last thing on paired t-tests is what's in the output. So very, very similar. We have descriptive statistics on both sets of measurements. So this one is comparing two different jumps that the same people, we collected the jumps on the same people. And we said, what is the mean of their jump? I don't know what we're actually measuring because, again, this was taken off the internet. But we can see sample size is the same because it's the same people. And then the standard deviation, nice and tight, right? Both of these values are fairly similar to each other, which usually we would then have some R correlation coefficient to tell us if we have a strongly correlated pairing effect between our measurements. And then the paired samples test would tell us if we have a significant difference between our groups or not. So in this case, this is telling us what the mean difference is. That's the one thing I hate about paired sample t-test is it says mean and not mean difference, which is really annoying because it's not the mean. But if you took 2.4815 minus 2.5155, you would get this value. So the order in which these are listed is what dictates the sign. So if we said jump 2 minus jump 1, this would be a positive value. So in this way, you can see which jump had the higher whatever we're measuring, right? In this case, jump 2 had a greater mean than jump 1 because we ended up with a negative mean difference. But same old, we can calculate confidence intervals to tell us where the true mean difference would exist in a population. We have our t-statistic, degrees of freedom, woo, and our p-value. So in this case, do we have a significant difference between the means or no? What do you guys think? Yes, if you think significant, no, if you think not significant. Chat. Morgan says yes. Does anyone concur? Yes, we have one person who concurs. Yeah, and we would have a significant difference, right? Because P is less than 0.05. How would we report this if I was asking you to write it in your activity or on a test? You can type this one in the chat if you want to.
Why don't you just reject the null?
We'll reject the null, yep. But how would we write the p-value? It's 0.000. Can we write it like that? No.
It's less than 0.01.
Yeah.
Or
Yeah. You and Tiffany both are correct. Right? So when you see 0.000, you have to write p is less than 0.001 because there is still some chance of error, but it's just small. Okay. So in this case, whatever we're measuring, I don't know, the intervention had a significant effect on the dependent variable outcome that was measured. Okay. All right. We're doing good on time. Just rounding out a couple more concepts that you guys will have practice calculating this week. Like significant differences are great. But there is one thing that I've noticed more and more as I've read more and more research articles, especially like in the PhD program I'm in. I literally read like 5 to 10 research articles a week, just for what my classes demand. But statistics wise, it's always a good idea when you're reporting your results to indicate what the meaning of the differences are. So more often than not in kinesiology research, we're going to be comparing two different means or two different samples, right? And we know from a t-test that we can report what that mean difference is and if that mean difference is significant or not. But how big is that significant difference? Okay, so if I go back to this slide here, we can see that the mean difference is 0.034, and that was significant. This is a very, very small difference between means. These numbers are practically the same, right? But we had a significant difference. But is that like, does 0.034 units of whatever we're measuring, is that really significant, or was that an effect of the sample that we collected? So that's where we get into the magnitude of the difference. And that's where we say, what is the actual importance, or what is the weight of the mean difference that we find? So this is different from a p-value. Usually we refer to this as the effect size. So in t-tests, I think there's a box we can click for the effect size. This is something that we'll actually look at in ANOVAs, where there's a box that you could check in the procedures where it's like estimates of effect size. So effect size is primarily what we're going to use. It's called omega squared in an ANOVA. We just call it effect size in a t-test. We can also look at change in improvement, which is looking at a mean difference as a percentage. We don't really look at this one in this class just because you guys already have enough to remember. But the magnitude of the difference just tells us what does the difference mean? Is it large? Is it small? Is it a moderate difference in terms of the units we've collected? And so for our t-tests, when we have two samples, we can take the mean difference and then we can divide it by the standard deviation of the control group. If we don't have a control group, we take the pooled standard deviation, which I go over in the activity this week, but that just means you take the standard deviation of everybody. So it's pooled. But we can calculate the effect size, and the values of the effect size are usually going to be between 0 and 1. Weiner et al. Found out or kind of established these values and what they mean in terms of what the difference actually is, right? So if we kind of went back to our t-test example, this output, where we had a difference of 0.3 that was significant, we could then look at the effect size and say, okay, well, how big is that difference really, right? And in our case, we might say that it's a small difference, but the effect size is not often reported as much as it should be, which is what I was going for when I started talking about the research articles that I've read, because it's not commonly noted, and I'm not really sure why. Maybe it's a word count thing for different journals, but the effect size tells us if the significance carries any weight. We could have a significant difference, but the difference between the means could be super, super small. And in terms of the sample or the population of interest, okay, cool, it's significant, but did the intervention really, really change anything? Right? So that's why effect size is important. It will highlight how big of a difference we actually had in terms of the variability that was within the samples we collected. Okay. So that is effect size. We'll keep revisiting this over the next few weeks. But you guys will practice calculating that in your activity this week. And then the last thing I wanted to talk about, we're coming back to it, power, sample size. Ooh, okay. This is another thing that's not often reported in research. But remember, power is a test or statistical test's ability to detect a real effect, right? It's the probability that we are going to reject the null when the null is false, okay? So if you recall, we had our truth table that had 4 different options. And we had type 1 error, which is our alpha, type 2 error is our beta. Beta just represents the opposite of power, which means that we would accept the null when the null is false. Okay, so there are 4 dependent factors, or 4 factors that kind of affect power. That's the alpha level set by the researcher, because remember I told you guys there's a trade-off between alpha and beta, right? If you increase your allowed error, or your allowed type 1 error, alpha error, you decrease type 2 error because you can only make 1 error at a time, okay? So alpha is 1 factor. Typically, it's not going to have that big of a weight on type 2 error because you set alpha before you run your statistical test. So the value doesn't change, that you determine that, but it does somehow affect beta, which I'll show in an example in a graph. We also have the difference between the 2 means. That's inherently what we're trying to look at with a t-test. The standard deviation, and as well as the sample size. Sample size is going to be the easiest way to increase power. Okay, if we increase power, that means we decrease the chance of type 2 error. So usually we say that we want power to be about 80%, which I think I list somewhere later, so it's written down somewhere. But 80% means that there's an 80% chance that we're going to reject the null when the null is actually false. And again, sample size is the best way. So usually what people will do is they have a research question, they create some type of methodology, and then they say, all right, let's pilot test this, let's get some data, let's practice analyzing that data, and then let's see what the power of our data is. And based on that power, you can see, do we need to increase our sample size, or do we need, or are we good? Like, can we stop with the level, right, that we have? So two go hand in hand. But we're
Natalie, I have a question.
oh yeah, go for it.
What was the 80% you were talking about earlier?
That's
kind of
the
disreferenced.
that's the power, the probability of power that usually we try to aim for.
Okay.
So if you think about it as in terms of a probability, right? We want an 80% chance that we're going to detect a real effect, right? Or we're going to reject the null when the null is false. That would result in a 20% chance that we would make a type 1 error, which we usually want to keep on the low side. But if we're calculating it, we can look at the means of our control group and experimental group. So I'm saying X1 is my control group, X2 is the sample of my experimental group. And let's say X1 is our ideal. That's kind of like, this is what the population should look like, right? So within this sample, we say we've got some level of confidence that has alpha and 2 tails. And if sample 2, or the mean of sample 2 lands somewhere within this area, we would accept the null and say that the means are relatively equal to each other. Right? If sample 2 landed somewhere on the outside of that confidence level or in our region of rejection where alpha is, that's when we say the means are likely significantly different from each other, such that these are representative of 2 different populations. Okay, so this part, you guys have seen this drawing before. Okay, the distance from our control group mean to the boundaries of our region of rejection is a z-score representative of the probability that alpha has, which you've also seen before, right? Z for a 95% confidence interval when we've got, or confidence level when we've got 0.025 in both tails gave us a z-score of 1.96. Right? So the distance from the mean to this region of rejection boundary has a certain z value. Now let's say that we found our mean of sample 2 and it landed out in this region. Okay, so it's in our region of rejection. The distance from this sample mean to wherever the boundary of alpha was on our control group also has a z-score, okay? And that's going to be the z for beta. So beta, again, is our chance of type 2 error. So you can see how the trade-off exists between these two, right? If we increased alpha, that means we're technically moving this yellow line inwards, which decreases the area of beta. If we increase beta, then we're decreasing the area that's given for alpha. Okay, so it all kind of floats around this line. But we're looking at what is the difference of these means from this critical value or this point that we have determined would tell us if we have a significant difference or not. Okay, so the area to the left of whatever the z-score for beta is tells us the probability of our type 2 error, which usually we want to keep at 20% or 0.2. Okay, and I go through how to find the z-score for that, I think in the activity video or the activity video. But the opposite of this, the rest of the area under this curve would be our power, right? Or 1 minus beta. Okay, so we can end up, like we can use the difference between our means to figure out our t-statistic, right? Which is technically just the difference between our error types, which is wild. Okay. So the difference between these two means is the actual sum of the distance of both of these means from the region of rejection boundary that we've set. prior to actually running the test. There's an equation. We don't have to actually draw this out all the time, okay? But in using this relationship, we can say that Z beta, or the Z-score, the probability that we're going to make a type 2 error, is just the difference between the means minus basically the probability of our alpha as a Z-score. Okay. All right. So this is just everything that I just said in words. If you like to read words instead. Okay, so I'm just going to skip over this slide. I usually just give both just in case people like both. This is the equation that we can use, though, to tie in our power information to calculating the size of our sample that would be sufficient for giving us the greatest power possible, which, like I said, usually power should be set at about 80. So using our Z table, we can figure out what Z beta is based on the power that we desire. So if I wanted 80% power, that means the chance of a type 2 error, the chance of beta would be 20%, or 0.2 if you're looking at it in terms of area under the curve. So I could look at my Z-score table and figure out where 0.2% would be. That would land at a certain Z-score, and that's the Z-score I would input into this equation. And there's butter again. Cat butt. Okay. If I wanted a power of 85, right, that would change Z. So whatever the power number is that I give to you guys in the example, you will have to figure out what Z is based on that power level, right? And power is just 1 minus beta. If you know the probability of beta, you can find the Z-score for beta, okay? But pretty much you just plug all of this in, plug and chug. You'll get some examples in the activity this week, so it should make a little bit more sense. But that's how we can use power to tell us how big of a sample size do we need in order to achieve this power. In which case we're just trying to maximize the chance that we're going to show that there's a significant difference when there really is one. Woo! All right. Last slide. I just want you guys to notice that there's a pattern that we keep having here with this whole statistical inference stuff, right? Where we have some sample characteristic in the numerator, and then we have the standard error, which is basically telling us what the deviation from the population mean is, right? So we are inferring, where's that pointer? We're inferring sample onto population by using this, this pattern here, right? So when we had Z-scores before, you guys remember Z, we said, what's the difference between means over the standard deviation of the population, which is basically standard error, right? For Z-skew and Z-curt, we said, what's the sample skewness or sample kurtosis divided by the standard error? Regressions, what's the difference between the sample slope and what we would expect the slope to be in a population in terms of being able to predict a certain dependent variable given relationships with independent variables, or an independent variable if you have bivariate regression. Okay. T-tests, if we're using a single sample t-test, we said what's the difference between the means over what we would expect the difference to be in the population. Same thing for if we have two samples, right? So that's statistical inference. That was the whole point of the lecture 2 weeks ago, right? Is to show us that we take sample information. The sample information that's in the numerator actually kind of tells us what we're calculating for or what we're solving for. But the standard error in the bottom is just telling us how far away from the population would this characteristic be. So we can look at skewness, we can look at relationships between variables, we can look at mean differences, but they're all drawing back to how does the sample compare to the population. Okay, that's our generalizability, external validity concept. Okay.
Natalie, what's the difference between those two different types of t-tests? The first one is sample.
The first one is a one sample t-test where we have an estimated population mean and a single sample.
Gotcha. And then the second one's two populations?
Two samples.
Two samples.
Yeah.
Okay.
So they could be between between subject or within subject.
Gotcha.
Yeah. So with that, we are at time. Woo! That was a lot. You guys had some good questions today. Does anyone have any questions before we leave?
It's not really a question. I was wondering if you just go up like 2 slides. So I want to make sure I got the blanks right for one of them.
Yes. Was it this?
Calculating power. Yes. Okay.
Oh, there was blanks on this one. I'm so sorry. Usually I remind myself by underlining stuff on slides.
Okay, thank you.
All right. No problem. Okay, I'm gonna stop recording just so it's not awkward.